Okay, if that's the evolutionary picture of what babies and children are all about, you might expect to see some of this reflected in children's brains. And in fact, you do. We could have the video. This is actually a video that shows work done right here in Chicago by Peter Huttenlocher. And what this shows is the development of connections in the brain over time. And what you can see very generally is that early in development, children are producing more synapses, more connections between neurons. And then what happens is that at a certain point in development, rather than producing lots and lots of new connections, what children start doing is strengthening the connections that work and pruning, getting rid of the connections that don't work and that aren't reinforced. And you can see that this happens in at different time scales for different parts of the brain. So the visual part of the brain, being able to see, that's developed by the time children are about a year old. The part of the brain that's devoted to language, the auditory cortex, sensibly enough, that isn't finished connecting until children are about 5. Now, it might seem as if this pruning is a bad thing, but if you're thinking about this transformation from a protected research and development person to an executive, pruning is actually a really good thing. The pruning is what lets us go out into the world and act in a really effective way. Just do the things that we know how to do well, really, really well. But it has a downside, and the downside is that it doesn't let you learn as much. It doesn't let you be as flexible or change as much. So what the brain development suggests is we have this early period, 0 to 5, in which we're exploring the world, finding out what we need to know, and then this later period when we take what we need to know and use it to do things really well. And if you look at the last line on the graph, that's about a particular part of the brain, the prefrontal cortex, that seems to be particularly involved in things like executive planning. So it's sort of the chief executive office of the brain. And you can see that that part of the brain continues to develop much later than any other part of the brain. We think now it's not finished until mid-20s. By 31, it's sort of supposed to be done. But interestingly, that's actually the last part of the brain to be finished developing in childhood. Okay, so if you look at children's brains, you see very much the same picture that you see from an evolutionary perspective. There's this early period in which there's tremendous possibilities for learning, for exploration, for flexibility, for change, and then a later period in which children are honing in on the particular skills and particular abilities that are going to be important for them later on. All right, get back to the big questions. So one of the big questions that we ask as philosophers is, how is it that human beings get to ever figure out the truth about the world around them? That's one of the great questions that, going back to Plato, we philosophers have asked. And what we started discovering is that that process of finding the truth is something that starts and in fact has its highest achievement in that first 5 years. That may sound like a crazy thing to say. How is it that children could be learning so much so early? What would we equip this R&D department with? Well, it turns out that children are using a lot of the same techniques to learn about the world that we scientists use. They analyze statistics, and they do experiments. Now, that may sound sort of crazy. If any of you have, I assume you've heard from Jim Heckman or from some of the serious social scientists, you know that understanding statistics is hard even for adults. But of course, when we do statistics, we're doing it explicitly. What we've discovered recently is that even babies understand something about statistics implicitly. How could we ever possibly know this? Well, we can exploit the fact that babies look longer at things that they think are surprising and unexpected than they do at things that they expect to happen. They're more interested in new things, unexpected things, strange things, than things that they actually expect. And we've used that as an incredibly powerful technique to find out what babies think. So this is work that Fei Xu, who's a colleague of mine at Berkeley, did. What she wanted to do was use this technique to see what babies thought about statistics. Now, a basic statistical idea is the idea of a sample representing a population. Here's how Fei actually tested this with babies. Can we see the video? What she did was she showed the babies a box full of ping pong balls.
Let's take a peek.
And these are 8-month-old babies.
Look.
What the babies see is that the box is either mostly red with a few white.
What's in the box? What's that sound? Look, baby. Look.
Or mostly white with a few red ping pong balls. Now here's what babies see next. They see the experimenter now take a sample out of that box.
Look at this one.
All right, so there's one white, one red.
See those? Look at that one. See this one? Look, baby. Look.
Okay, so now that makes sense, right? That's what you'd expect. If it's mostly red, then you'd expect to pick out mostly red balls. But now, here's the next thing that we can show to babies.
See this one? Look at those.
Okay, now hopefully you guys will be starting to think, this looks like it's less than 0.05 significance.
Look at this one.
This isn't a random event.
Look.
That event doesn't make any sense at all. There must be something else that's going on. Well, that's what 8-month-old babies do. So 8-month-old babies will look longer at this second event where you pull mostly white balls out of a mostly red box than if you pull mostly red balls out of a mostly red box. Even though it's only statistical, you could produce this many white balls from a white box. So 9-month-olds are already sensitive to the statistics of the world around them. We've shown the same sort of things for older children. So now we're looking at preschoolers, 2, 3, and 4-year-olds. Again, how could we ask preschoolers whether they understood something about statistics? And in particular, we wanted to ask, would children draw conclusions from these statistical patterns? What we did was invent a machine that we call the Blicket detector. This is this box that lights up and plays music when you put some things on it, but not others. Actually, the secret is that there's a graduate student behind the curtain who's pressing the button to make it go. My son, who was a pilot in this, tried to figure this out for 6 months before I told him the answer. I think he's just getting around to forgiving me. So what we did was we did an experiment where we started out by simply asking the children, these are 4-year-olds, to tell us how to make the machine go. And most of the children sensibly thought that you ought to make contact between the block and the machine. You should put it on the machine to make it go. Then what we did was we showed them some evidence. So we showed them 2 blocks. The red block, so the red block makes it go 2 out of 3 times, and the blue block makes it go 2 out of 6 times. But the red block doesn't actually make contact with the machine, the blue block does. Now, if you were a good statistician, what you'd say is, oh, my original idea must be wrong. I have to have a new hypothesis, because after all, 2 out of 6 is less probable than 2 out of 3. What we did then was we simply asked the children. We didn't ask them, could you tell us which has the highest conditional probability? We just said, make it go. And sure enough, 4-year-olds would choose the red block rather than the blue block and did it in proportion to the probabilities. So these 4-year-olds who aren't yet adding or subtracting very well could calculate probabilities, make the right causal conclusion, and change their minds and get a new hypothesis as a result. Now, we think that not only are children doing this by means of statistics, we think they're also experimenting, as you might imagine, if they're little scientists. So what we did, and this is Christine Laguerre at the University of Texas at Austin. You want to start doing the tape? What she did was she showed children our Blicket detector. First, she showed them that there were 2 red and 2 yellow ones. And then she showed them that one didn't work, gave them the box, and just said, can you figure this out?
This makes that light up the box.
Mm-hmm.
How about this? That makes the other side. Ah. Oh. Nothing. This one's lighting up and this one's not. So that means it's making this light up. I don't know. Oh no. Oh, it's because this needs to be like this. And this needs to be like that. That's why. Oh. Oh, the boxes are the wrong way.